Okay, we're going to use this simple simulation to look at Ohm's law in a little bit more detail. As you've already seen, Ohm's law is a simple equation that says the voltage is equivalent to the current times the resistance in a simple circuit. Now, in this simulation, we've got our voltage source, which is this little battery here that's labeled 1.5 volts, and we see a little dimple on the one end that represents the positive side of the battery. The other side would be negative. Now, conventional current flows from positive to negative, which is a little bit confusing because we actually know that electrons are the ones that are actually in motion, and they of course are repelled from the negative side of the battery and attracted towards the positive. So electron current is actually opposite to conventional current. Now, it's a little bit confusing, but honestly mathematically it makes no difference, so we've always just kept it to the conventional current, which is from positive to negative. Now, the second thing we need to understand with circuits, you will get a current flowing, a conventional current or an electron flow, as long as there's a complete circuit that flows from positive to negative. As long as there's a potential difference along the path, the current will flow. So here we see a complete circuit, only one wire. It travels through this pinkish device down the bottom, which we're going to call a resistor, and I'll explain that in a second, and all the way back to negative. So it represents a complete circuit. Current will flow, and in fact the way I've got it set up, it tells you at the bottom that the current is 7.5 milliamps. Now I can adjust the voltage in the circuit, and if you think of voltage as electric pressure, if I crank up the pressure in the circuit, just like on a hose in your garden, if I crank up the pressure, the flow, which is our current, increases. It goes to 15 milliamps. If I keep cranking it up, add another battery, the flow goes to 22.5 milliamps, and so on and so on and so on. I'm going to turn the sound off. So as the voltage or the electric pressure goes up, we see immediately that the current increases. Now what about the little pink device? We call that a resistor. Now a resistor is a simple device in circuitry used to regulate current. A lot of components in electric circuits require specific amounts of current. Remember, current is a flow. It's a flow of electrons, and that creates friction. It can generate heat. Sometimes heat is wanted, sometimes it's bad. It can destroy components. So we want to regulate the current with these resistors. Very, very common component in circuitry. So you can see that the resistor is represented by this little cylindrical shaped device, and these little black dots represent some sort of impurity inside that resistance. So the electrons are flowing basically unimpeded through the metal wires, very, very good conductor, and all of a sudden they get into a poor conductor, which is represented by a resistor. Now, the higher the resistance, the slower the flow. Now watch what happens when I crank up the resistance. First of all, the current diminishes. You can see that in our equation. And as I crank up the resistance, you see the impurities gets greater and greater and greater. So it resists the flow of the electricity. It resists the flow of electrons as they smack around inside that resistor trying to get through. So smaller resistance have fewer impurities. Now back in the day when they made resistors, they used to just use long wires, long skinny wires. The longer the wire, the more friction that was involved, the lower the current. And they used to just coil them up into little resistors. But we've got a little bit fancier now, and they're basically just impurities. So there's the first step. Now what I'm going to do is simulate how we come up with Ohm's law. I'll keep my resistance at 200 ohms, and what I'm going to do is adjust my voltage and make a record of voltage versus current. So we're going to create a data table. So originally my voltage is 0.5 volts. My current, as recorded here, is 2.5 milliamps. So I'll record that in a table and keep cranking it up by half a volt. So at 0.5 volts, my current is 2.5 milliamps. At 1 volt, my current is 5 milliamps. At 1.5 volts, my current is 7.5 milliamps. At 2 volts, my current is 10 milliamps, and hopefully you're seeing a pattern. It's in fact a nice direct relationship. If I double the voltage, I should double the current, provided I'm not changing the resistance. So here I've got 2 volts. If I crank it up to 4 volts, I end up with 20 milliamps. So remember, at 2 volts, I had 10 milliamps, double the voltage, double the current. Direct relationship, 20 milliamps at 4 volts. So at 8 volts, we would predict it to double again to 40 milliamps. And lo and behold, 8 volts is 40 milliamps, and notice my diagram. Large voltage, large current. Resistance is not changing. So let's take a look at our data table now and see what we can come up with. So you can see on the left of the screen, I've constructed a data table where I've recorded my voltage and my current from that simulation. And if you'll recall, at 0.5 volts we had 2.5 milliamps of current, at 1 volt we had 5 milliamps, and we cranked it up all the way down to 8 volts where we had 40 milliamps of current. And we predicted a direct relationship because we can see that as we double the voltage, as I go from 2 volts to 4 volts, we double the current. It goes from 10 milliamps to 20. Now I want to construct a graph of voltage versus current, but the current has to be in amps for this to have some meaning at this stage. So I've made one more column where I've converted my current to amps from milliamps. So I've taken all my milliamp readings and divided them by 1,000 to get amperage. Now I'm going to make a graph where V is on the y-axis and current in amps is on the x-axis. It'll be a very simple relationship, and we'll plot the data. It will look as follows. So we see that when we plot voltage versus current in amps, I get a direct relationship. You see my dots line up in a nice straight line that passes through the origin. As with any graph, we'll construct our best fit line right now. So there we see our linear relationship. Voltage is directly related to current. Now what about the slope? Well, let's start with the equation of the line. We know in mathematics the equation of any line is given by y is mx plus b. Any straight line, which is what this is can be written in slope-intercept form. Y is slope times x plus the y-intercept, which is b. So let's write that down. So I've written down my slope-intercept form. Y is mx plus b, where m is the slope and b is the y-intercept. However, in physics we don't have y-x graphs. We have specific graphs, and this is a voltage on the y-axis versus current on the x-axis. So my variables instead of y will be capital V for voltage, and instead of x it'll be capital I for current. Now I've already written in that my intercept is 0. It goes right through the origin. So really my equation simply becomes V is slope times I. So all we need to do is figure out what that constant value of the slope is. Notice that the steepness of that line never changes, which is why we say it's constant. So to figure out slope, we simply do rise over run, and we can do that right on our graph. So we can see my rise is 8 volts and my run is 0.040 amps. Notice I've made the slope, the rise and the run as big as possible so that I have less error. My slope will be 8 volts divided by 0.040 amps, which is 200 volts per amp. And it turns out that volts per amp, that constant slope value, is equivalent to an ohm. So 1 ohm is 1 volt per amp of current. So our slope of 200 volts per amp is the same thing as 200 ohms. And if you'll recall from our simulation, that was actually the value I have given to the resistor. And you can see I recorded it up top. The resistance used in the sim was 200 ohms. So if I write my equation in full, I get the following. I get V is 200 ohms times I, or V is equal to Ri, or finally if we just rearrange it, V is equal to IR, Ohm's law, where R is the constant of proportionality known as the resistance.